Welcome. We have been discussing about different relaxation schemes, line relaxation and block relaxation schemes with a focus to solve the matrix equation not in a pointwise manner. That means, each element of the x vector will be updated through the iterative schemes, not going in that way, rather trying to identify a part of the solution vector and try to update it at one go and then do it for different parts. So, we have discussed about alternate direction implicit method, which I said is a line relaxation scheme. In ADI, the coefficient matrix A is decomposed into two parts, H plus B. H comes from discretization in x direction, Y comes from V comes from discretization of in y direction. So that now the pentadiagonal matrix problem can be decomposed as two problems sort of. This is ADI is typically for two dimensional Laplace equation problem. So, instead of AU is equal to F, we can write HU plus VU is equal to F, and HU has x directional discretization, VU has y directional discretization. So, this is pentadiagonal, A is pentadiagonal, H is tridiagonal, V is also tridiagonal. The idea is first solving HU is equal to F minus VU star and then solving. So, this is HU k plus half is equal to VU k, rather last updated value, and then solving VU k is equal to F minus some F star 1 and F star 2 some value minus V minus H U k plus half and updating it. So, this is broken, a pentadiagonal matrix equation is broken into two tridiagonal matrix equations, and we know that tridiagonal matrix equations are much faster to solve. Similarly, large matrices can be decomposed into small blocks on which direct solution methods, if not direct solution method, some of the iterative solution methods which are easy to implement can be used, and iterations are performed over blocks of the solution vectors. So, instead of solving the entire matrix equation, we will break the matrix into small blocks and try to solve for each of the small blocks. And while solving for one particular small block, we will assume that the Gauss value is obtained for the vectors which are associated with the other small blocks. Only for the diagonal part we will solve it. For off diagonals we will assume the Gauss value for the blocks, and then iterations are performed over blocks of solution vectors. This can be of help when the matrix is very large, say a million by million matrix, which is very often we encounter million by million matrix. It will be much difficult to store the matrix. We need some storage algorithm to consider the sparsity of the matrix and store the right non-zero values, because storing zero values will add a redundancy in the overall algorithm. And also, when you are using some storage algorithm that only non-zero values and their right pointers are stored, you have to use a memory management methods also. So, for a large matrix, the storage and memory access will be much difficult, much complex say, and it can be easy if we break down into small blocks. We will only store the small blocks, and doing any memory management will be easy also in the small blocks. So, this is not only memory management done by the computer, but it is also important when we think of that a part of memory management is actually being done by the processors and the computer architecture also. So, it is accessing memory at the RAM, putting some of it in cache, accessing data from the cache, starting with a memory location and going along the pointer to the new memory, new element of that memory. All these things, this will be easy when we break it into small pieces of blocks. Direct inversion of block matrices can be possible. We have seen that direct inversion is usually a costly method, except a TDMA. If we have to use something like LU or some algorithm like Cholesky, etc. These are costly methods, and they take almost n, if consider an n by n matrix, they take almost n cube operations. So, if for a million by million matrix, it will be extremely large number of operations, we probably cannot do it in any practical purpose. But if we break down into small matrices, we may get 100 by 100 matrices, where n cube operations is still possible. So, direct inversion is possible for block matrices, and parallel algorithms like Schwarz method can be designed. Idea of parallel algorithm is that you divide the big matrix equation into number of small matrix blocks and ask different processors in a computer architecture to solve different blocks in parallel. Nowadays, we get computers with dual core, 16 core, even 32 core processors. 32 processors are present in the computer. So, ask each processor to look into one block, so that the 32 small blocks can be done in parallel, then you can save lot of time. Instead of going from 1 to million, maybe each processor is going 1 to 1000 rows, and considering 32 processors, 32,000 rows are done in the time in which you are supposed to do 1000 rows. So, this is a parallel process. So, we will discuss about parallelization in a few of the later lectures, which also can be done once we think of a block partitioning of the matrix, or when we think of block relaxation schemes. So, how will it be? Let us consider an equation A x is equal to b, the matrix A and the vector x, and the solution vector b, and the RHS vector b, such that A is divided into number of small matrices, all A11, A12, A13, APP, all these are matrices. A is decomposed into number of small matrices, each is a block matrix, and X is decomposed into P blocks, xi 1, xi 2, xi 3, xi p. X has maybe X has 10,000 elements, and each of them there are 10 blocks, each has 1000 elements. So, all these xi's will be added up to give us X, and similarly B is also decomposed into some small blocks. LHS of the equation corresponding to any row now can be expressed as, right hand side is summation of A and multiplication of A and X for one particular row will give Ax of that particular row. Ax is nothing but Aii is Ii. So, what is the first row of this equation? If we go back, that we are solving Ax is equal to b. The first row will be Aij xj is equal to bi. If we think of a block partitioning, this can be also expressed as summation of A 1i xi I. So, this is first row A1j bj is equal to this summation of A1i xi I is equal to beta 1's the entire equation's first row of that, because this is also a matrix, also a vector equation. Beta 1 has number of elements, the first row of this particular element. So, we can say that the left hand side of this equation, which is A1j xj or Aij for any particular row I, can be expressed as Aij xij into xij. Let us split A into A similar to splitting of Jacobi GS or S-Schwarz scheme of the full matrix, that is A is equal to D minus E minus F, D is the diagonal, E is the lower triangular, F is the upper triangular matrix. Based on our scheme, whether it is Jacobi or Gauss-Seidel, we will multiply the last guess value with E f or E minus E plus f, we will say that. But we can revise the discussion on basic iterative methods. This is the standard splitting for Jacobi or Gauss-Seidel. In a block decomposition, D will be the blocks containing the diagonal terms. Earlier, in a general splitting of A for a basic iterative point relaxation scheme, D only contain the diagonal elements. Here, instead of diagonal elements, they are containing the diagonal blocks. E contain the lower triangular blocks, F contain the upper triangular blocks, and E and F both has diagonal element 0. So, instead of splitting it by element, we are splitting it by blocks of matrices. So, the Jacobi iteration step is dxk plus 1 Ef plus kxk. If we consider the block splitting of the matrix, this will be A11, A22, etc. So, this is one block of matrix is multiplied with the solution value that we have to find out, and E plus F will be multiplied with xk, which is the last available value. So, this is aii xi k plus 1 E plus F xk I beta I. Here we are writing xk, not we are writing xi, because xk contains the entire solution vector, and entire solution vector has to be multiplied with E and F, and each E and F has diagonal 0. So, that particular vector which is xi k is not being multiplied with E and F. Note that the structure of the diagonal matrix D and that has been utilized here, that the diagonal matrix is aii, is the structure of diagonal matrix, is the diagonal blocks here. This matrix is D is not actually a diagonal matrix, rather a block diagonal matrix here, and we also use the fact that E and F has diagonal entry 0. So, we can write this using the last relation, the relation we have developed here. We can write xi I k plus 1, which is the new updated block of solution vector. This is not a single solution vector, rather this is a block of solution vector. A number of x's are involved in this vector, is equal to aii inverse E plus F x k plus aii inverse beta I is equal to 1 to p. Now, we can see that this is not a direct solver points or relaxation scheme. So, that this is D inverse. So, this is a single 1 by the diagonal value, this is inverse of a matrix. However, as we think of dividing the matrix into large number of matrices, a large number of matrix blocks, these matrices are basically smaller matrices, and we can easily find out their inverse. It will be not that complex. Complexity is usually in terms of what are the order of operations we need to do to find out that inverse. Inverse finding is same like Gauss elimination scheme, takes n cube operations. As we have broken down the matrix into small blocks, the number of rows in each block is very small. If we think of million by million matrix, maybe we have 1000 rows in each block. So, this will be much less time consuming, number of steps will be less to find out aii inverse, because this is a small matrix, the number n is smaller here. And we have to do it for all the blocks, starting from first block xi 1, xi 2, xi p, we have to do it for all the blocks, and then again iterate it. This is an iterative method which we are discussing. This particular equation is very similar as the basic Jacobi iteration step, and if we can think, this is actually the Jacobi iteration step. Why? Because for all off diagonals we are using xk, which is the last iterative value, and aii inverse, instead of aii we are solving an equation like that. Instead of directly finding inverse, we can use something like a Jacobi iteration also. So, this step can be exactly same as Jacobi iteration step if we use Jacobi iteration for finding aii inverse, but we can, because the aii matrix is smaller, we can use some of the direct solution method or some other method to do it also. However, if Jacobi iteration converges, this step should also converge. So, the iteration is not in aii inverse explicitly here, iteration is on finding out xi k plus 1. This solution is done in some other method, but iteration is over that fact that xi k plus 1 is found out, and this is being iterated again and again. So, this iteration must converge if the Jacobi iteration converges here. we can see an example of block relaxation. This is the domain where we have 32 points and a finite difference matrix of is a pentadiagonal matrix. So, along any line there are 5 elements only and they are near the diagonals, 2 super diagonals, 2 sub diagonal and 1 diagonal line. This is the mesh from which we got the finite difference matrix. Now, we are doing a partitioning here. This is one group, this is one group, this is one group, and these are the 3 diagonal blocks we will get. So, block of x vectors. So, that is x 1 to rather instead of x we should write u, we are trying to solve a u vector. So, we are trying to solve a u is equal to b say. So, xi 1 u 1 to u 12 is one group of block of vectors, this is xi 2, u 2 to u 24 is another group, or I think I should rewrite it, this is xi 2, this is xi 3. So, what is that? That this is one particular block of vector, this is one particular block of vector and this is one particular block of vector. So, where the matrix I will get, that matrix will be decomposed into several blocks, and these 3 are the diagonal blocks which will be directly multiplied with xi 1, xi 2, xi 3 when we are solving iterating for xi 1, xi 2, xi 3 etc. So, these are the A1, A11, A22, A33 the diagonal blocks, and there are few off diagonal blocks. It is important to look that these 2 off diagonal blocks are basically 0 matrices. So, we can eliminate some of the off diagonal blocks also from the calculations. And A, the net, the actual matrix A, when we, because we are solving the matrix equation A u is equal to b, this A matrix is sum of all the small matrix blocks. It is also possible to form blocks with the overlap. That means that maybe this line is being shared by 2 different blocks. So, you can think of another blocking like this. So, this is one block, maybe this is another block, and or rather let us do it like this. Maybe this is one block, this is one block, and we can say that this is another block. These blocks have some points in points common to them, and we will see that overlapping blocks are important to maintain continuity of the solution as well as to have some of the parallels algorithms can only work with overlaps. So, we will see about the overlaps later. The best thing of overlap is that when you will try to solve in this domain, this point we will see the full stencil or full discretized row for if there is an overlap considered. We will come into the overlap part later, but it is also possible to form the blocks with overlap. That is what is important to keep in mind here, that this is a typical blocking with non-overlapping blocking. What we are showing here is a non-overlapping blocking, but we can also have overlapping blocking. Let V, so we will see the formulation of a block relaxation scheme. Let V I be a n into n I matrix, and V I is basically the columns of identity matrix of up to n I will consider V I. So, it will have n rows and n I columns. So, there are n I columns which are E j's and they represent the jth column of an n into n identity matrix. So, its V I is a truncated part of an identity matrix, where W I is chosen in another n into n I matrix with eta 1, E 1, eta 2, E 2 etc., where eta j represents the weight factor such that W I transpose V I is an identity matrix n I into n I, and this is required to map the solutions. V I will be required, or as well as W I, to map the solutions xi to the right x, say xi 2 I will take, which will be after xi 1, or we can write that x rather the u matrix, sorry, u matrix will be xi 1, xi 2, so on, xi a, xi p. So, if I find out xi 2, that will come in one particular location of U matrix. So, I have to multiply something with xi 2 to make it assemblyable to U matrix, which comes from these terms n 1 E 1 n 2 E 2. If there is, or E 1 E 2, if there is overlap, then if there is no overlap, then E 1 E 2 E 2. So, xi 2 into E 2 will keep xi 2 here. If there is no overlap, it will run there. If there is overlap, then maybe this is the location of xi 1, and from here we will start the location of xi 2. So, I have to multiply something with E 1. For no overlap between the domains, eta is equal to 1. So, the V and W are basically same in these cases. Now, the block Aij of a Nij matrix, which is an Nij matrix, can be given as Aij is Wi transpose A Vj, and similarly xi will be given as Wi transpose x. I have used x and u, mixed x and u in the discussion. Either x or u is fine, because we started with the problem A u is equal to b, but sometime I confused myself writing A x is equal to b. Both are matrix equation, be it u, be it x is the solution variable. However, in the present slides that I will upload, I will make either x or u, uniformly I will make it same. So, nevertheless, the xi I will go to the solution vector x we are discussing instead of u. Using this particular weight matrix W, similarly beta will similarly be mapped into B. So, this is the idea that you have the large matrix B, and a part of this, the large vector B, is say beta q. So, once you know beta q, this will be multiplied with W q transpose B is beta q. This will be multiplied like that. So, instead of multiplying W with beta, we are doing W is transpose multiplied with B, that will map B to beta. And if there are n blocks, we can write x is equal to I is equal to 1 to n V I xi I. So, this is how xi to V x mapping is through V, xi to x mapping is through V, and x to xi mapping is through W. They can be same for non overlapping case. For overlapping case, it will be W will have to carry an weight. Each component of Jacobi iteration can be rewritten as projection of the residual into in the overlap domain is equal to 0. So, we will get residual in a subdomain. If there are projections, then we will project if there is overlap, then the overlapping of the residual will be obtained. However, sum of the residual as projected to the main domain should be 0, and that comes as Wi transpose B minus Vi Wi transpose x k plus 1 is if j is not is equal to n Vj Wj transpose x k is equal to 0. If there is no overlap, Vi transpose Vi Wi transpose Vj Wj transpose, these terms are 1, right. If there is no overlap, V transpose W is again an identity matrix. V and W are same. So, this becomes an identity matrix, but if there is overlap, they are not identity matrix. So, this becomes the Jacobi iteration step, projecting that the new solutions, the residual from the updated solution and non updated solution, that residual must be 0 into the overlap domain. Now, we use the fact that xi is equal to Wj transpose x. So, we multiply Wi transpose with this and write xi is equal. So, whenever Wi transpose x is there, this is xi k. So, the iteration step will be written as xi k plus 1, which comes from here, and this is equal to W transpose A V is basically A I I. So, A I I, so this will give us A I I j k plus 1 is equal to A I j x j k, like that. So, this will be j I k plus 1 is equal to j I k, which we will again get here, plus A I I inverse W I transpose B minus A x k, and this is what we exactly do in a Jacobi iteration step. We get the mapping weight function W, and then multiply its transpose with B minus A x k, and then multiply with A inverse and add with j k. And now using the W's constructed, W and V constructed, I can get a general algorithm for Jacobi block relaxation scheme, which is k is equal to 0 to up to convergence, do it up to convergence. For each block, write A I I delta I is equal to W I transpose B minus A x k. Solve for delta I and then update x k plus 1 as x k plus V I delta I, because delta I is solved for j k plus 1 minus j k, that is in delta I. So, you have to multiply V I with that and update x k plus 1. For better convergence, instead of block Jacobi, we can think of block Gauss-Seidel, because each scheme is using the last iteration value of x in block Jacobi. In Gauss-Seidel, instead of using x k, it is using the value x, which is the last available value in the neighboring blocks rather. And you solve not only neighboring blocks, in the entire domain, the last updated value. You solve A I I delta I is equal to W I transpose B minus x, and update in each block, you update x like this. So, this solution can be done using GS or using Jacobi. If you want to do a full Jacobi in a block Gauss, full Gauss-Seidel in a block Gauss-Seidel, this solution should also be done using Gauss-Seidel. But however, when using this particular x, it is updated from the neighboring values. The neighboring values, which the neighboring blocks or the last blocks which are above the xi's, which are above this particular xi, particular block, will have the updated value, and the other one will have the last iterative value. This is very same as Gauss-Seidel iteration. Gauss-Seidel iteration needs less storage, because we do not need to storage x k plus 1 and x k separately. It needs less storage and also faster, because we are using the last recent value. However, the Jacobi method can be parallelized due to less data dependency, in that sense that once we have the last iteration value, we can go to the new Jacobi step, and if we are doing in different processors, none of the processors has to be aware of the fact that what is the updated value in other processors. Everybody is using the last iteration value. Gauss-Seidel, block Gauss-Seidel cannot be parallelized in that way, because it is data dependent. One particular block has to be aware of what happened to what is the updated value after the previous blocks in that, during that particular iteration. The blocks which came before this particular block has been updated. So, it is difficult to parallelize it. Similarly, Krylov subspace methods can have block operations, and they are often performed using block Krylov called block Krylov subspace methods. They are equivalent of Krylov space methods, but they are done for matrix blocks. And there is a block Arnoldi method, which starts with an unitary matrix V1 dimension n into p, computes the Heisenberg block matrix Vij transpose Vi transpose Avj, and then does an orthogonalization of it. That means, it from Av multiplies V with A and subtract the Vh, and then does a QR orthogonalization of W to find out W. W is Vj plus 1, Hj plus 1j, and comes with all the basis functions of W and V, but these are not basis of the Krylov subspace, rather they are basis of the Krylov block subspaces. This can be compared with original Arnoldi's method, which started with a vector V1. Instead of starting with an unitary matrix V1, it started with a vector V1 of unit norm and computed H and Heisenberg matrix and W by using vector vector dot product. Here instead of matrix, here a vector vector dot product is used instead of vector and matrix vector dot product, and also a matrix vector product has been used respectively. So, the products are little the process is little essentially similar, but instead of starting with a vector V, instead of starting with a vector V, they are starting with a matrix V1, that is the difference. This is Bloch-Arnoldi algorithm, and this is, if we compare with the Arnoldi method, it starts with a vector V1. So, this is the vector, these are the difference. It starts with a vector, here it starts with an unitary matrix. Here this is compared as a matrix vector product, and then it is dot with this. However, this is a vector matrix product, and then it is transposed with H. Similarly, the Wj computing is also different in Bloch subspace. So, we get the basis vectors for a block of Krylov subspace, of the block matrices. We defined IK as identity matrix, and we will see that the following relationships hold. Similar type of relationships which we got for simple point Arnoldi method. The following relationship holds that Heisenberg matrix HM is not a Heisenberg matrix, rather it has p subdiagonals, and it is called a banded Heisenberg matrix. All these are banded matrices, and a relationship like this holds, which is very similar to a relationship we obtain to get the Heisenberg relation between the Heisenberg matrix and the Krylov subspace basis vectors. Now, instead of a basis vector, this is a basis matrix. Instead of the Heisenberg matrix, this is a band Heisenberg matrix. But Krylov subspace type of relations are were applicable for the solution vector x earlier. Now, it is applicable for blocks of the solution vector xi's. The same idea, with the same idea, block full orthogonal method or block GMRES can be obtained. Block Krylov space methods obtain a group of basis vectors instead of a single vector in each step. So, instead of finding out basis vector, it gets a basis matrix, we can say, and the iterations can be done between the blocks of the solution vectors. Within each block, I can use even a direct solver. That is how this can give a faster solution, or this can be parallelized also. So, we have discussed about block relaxation schemes, also line relaxation schemes in last two sessions, and we can see that block relaxation schemes has a potential of parallelizing the solution, in a sense that the solution task will be distributed into number of computers which will operate together, and instead of one computer doing all this n square order or n cube order of operations, one computer will do less task and all of the computers will work in parallel, so that the computing task can be carried away in less time. Instead of one people carrying a load, if two people instead of one person carrying a load, if two people carry the same load, it can be much faster. So, that is the idea of block, that distribute the matrix into several blocks and use different computers to do it in parallel. That is one great advantage of block partitioning. This can be exploited for parallel computing, and we will look into it in the subsequent classes. Thank you.